Welcome to the physics class for February the 18th. As you can see, I am not at my home. I'm at the school and I can't go into my room because Martha stole my room. So those of you that are in Martha's class, I want you to wag your finger at her. I have to sit here in Miss Whitbeck Zacharias's room and it's cold in here, good grief. But oh well, I deserve it. Oh, thanks, Sam. Okay, I'm gonna remember that when I grade the next test. Okay, speaking of tests. So I trust that you noticed that the tests have been scored, including the partial credit. And the scores are now in Aspire. Those of you that turned in partial credit, it was a really good thing you did. It made a huge difference in your grades there. I was able to see in fact, in most cases, I could see that you knew what you were doing. You just made a silly mistake somewhere along the way. And as usual, I will be, I am generous with partial credit if I can see that that's the case. So the number that you see in Aspire is different from Canvas for a lot of reasons, as usual. I always scale things so that the number that's in Aspire is always on a scale of 0 to 100. And also I grade things on a curve. So if you were to calculate your percentage score on Canvas and compare that with your percentage score on Aspire, you'll see that the score in Aspire is higher. And that's because of the curve adjustment that I do. So several of you got 100% or higher. And it is, of course, possible to get higher because of the extra credit problem, which many of you got right. Those of you that didn't try it, you should have tried it. It wasn't that bad. Just because it's extra credit, that doesn't mean that it's impossibly hard. All right, so now, those of you that got 100% or higher, you don't need to do the test rework, but those of you got anything less than 100%, you have to do it. Even those of you that got 99%, you still have to do the test rework. You have to do all of the problems. And by the way, the extra credit problem is not extra credit in the rework. On the rework, it's a required problem. I am going to give you until the end of next week to do that. So it'll be due on Saturday at midnight, not this coming Saturday, but a week from this coming Saturday at midnight. Okay, I can't think of anything else. You guys got any questions? Nope. Okay. Then, oh, you like my coat. Oh, well, thank you, Rory. Yeah, it wasn't so darn cold in here. I don't know why they keep it so cold. All right, let's go ahead and move on. Okay, so in the test, there were some questions where I gave you some examples of different types of waves, and I asked you where there's a longitudinal wave or transverse wave. So I gave you like sound waves, and I gave you a wave on a string and a wave on the ocean. What about light? And in fact, before we discuss whether light is a transverse wave or whether it's a longitudinal wave, is it even a wave? What do you guys think? So I want you to type in the chat box in a private message so that nobody else can see it. I want you to type, do you think light is a wave or do you think it's a particle? Let's see what you guys respond here. Come on, guys, I need to see something here. So some of you realize that, that there is a trick to this question, okay? In fact, it looks like most of you realize that it's not such a simple question. Yeah, okay, very good. Now, some of you are saying that it can be both. Several of you have mentioned the concept of wave-particle duality, which is really mind-blowing, but we will definitely talk about that. Okay, so the first part of the class period today, I want to deal with that question. Is light a wave or is it a particle? Maybe both, I don't know, let's see. So if you were to talk to the person who is maybe the most famous physicist who ever lived, that would be Isaac Newton. If you were to ask him, he would tell you light is a particle. There was debate at the time. Isaac Newton was very strongly in favor of the idea that it's a particle, and there were other scientists who thought maybe light might be a wave. But Isaac Newton convinced them that light cannot possibly be a wave. And there are two very, very good arguments for why it is that light cannot possibly be a wave. So let's talk about those two very good arguments. Let me first just start off by showing you, let's talk about what Isaac Newton thought at first, okay? So let me share you my screen here. So this is the Newton theory of what light is all about. And let me go up here. Okay, so Isaac Newton thought that if you've got a light bulb here, in fact, let me just do a little bit, clean up here. Okay, so he says, so here's a light, actually they didn't have light bulbs back then, they just had flames. Okay, so here's a flame. That's a terrible picture of a flame. But okay, so what Isaac thought was that you've got these little particles and they're all flying away from the flame. And so he came up with this idea that you call a ray, and the ray is the path of the particle. So if you got the particle, it travels like that. So they travel in straight lines. And when these light particles hit something, they bounce off of it exactly the same way that a rubber ball would bounce off of some surface. And so then that's what we see. Now, the reason that they don't bounce off, well, let me rephrase that. If you look here, there are different ways that they could reflect. If you had a surface that was absolutely positively smooth, then what would happen is what you see on the left side here. You see these little particles of light, they come in, they hit the surface, they bounce off. And so the incoming angle and the outgoing angle are exactly the same, okay? That's if everything was perfectly smooth, but of course nothing is perfectly smooth. And even something that looks smooth, if you go in on a microscopic level, you'll find out that it's not perfectly smooth. All right, and so what's going to happen is the light comes in at this angle here, and it's going to reflect all sorts of different directions because different parts of the light are hitting different parts of the surface, and the surface is rough. So that's why you see diffuse reflection. So when I look over here, or actually when you look at my nice stylish coat that some of you commented on, okay, the reason you can see it is that the light is coming from the thing in the ceiling there, hitting here, and it's bouncing off in all different directions, and some of those directions just happen to go towards your eye. All right, so now if you do have something that is as smooth as you can make it reasonably, then the majority of the light rays will come off there, which is in fact what happens if you look at the surface of the water, or you look at a piece of glass or something, you do see that the majority of the light rays do come off at that angle there. So Isaac Newton's theory of the particle theory of light definitely corresponded with what was observed in real life, okay? So you can see why people might believe the particle theory of light. But why was Newton so adamant that light could not possibly be a wave? Well, the reason is because Isaac Newton knew a lot about waves and the way the waves behaved. And so Isaac Newton would look at a situation like this. So we've got some people standing here, and you can see their shadows. So if you look at their shadows, let me hang on a sec. Sometimes when I write on my screen, I touch the wrong button. Okay, so if you look at these shadows right here, you'll see the edges of the shadows are very sharp, very distinct, sharply defined edges. So Isaac Newton looked at that and he said, aha, that is proof that light cannot be a wave. because if light was a wave, you wouldn't see those sharp edges like that. So why would he think that? Well, there is a thing that all waves do, which you need to know about. This is a really important feature of waves, and it's called diffraction. And this picture right here is probably the best example that I was able to find anyway of diffraction. So this is a picture of a beach where the people who manage the beach, you know, the mayor of the city or something, you know, they rely on tourism for a huge part of their money. And so having a nice sandy beach is really important because people don't like rocky beaches, people like sandy beaches. And so these things that you see right here, those are artificially made things to break up the waves so that the waves don't come in and carry all the sand away. So without these structures here, what could happen is that the big waves come in and they pull all the sand out to sea, and then the tourists aren't going to want to come. Okay, so what they did was they constructed these things right here. So when the waves come in, well, some of the waves get blocked, and the waves that do come in, they don't come in with as much force as they would normally come in, especially during a big storm. And so it doesn't wash away all the sand on the beach. But notice something really, really interesting. If you look at a wave coming in, so here's all these waves out here. Those are all the wave fronts. If you look at the direction that the wave front is traveling, you see that when it comes through this opening in between these breakers here, the thing spreads out. Okay, same thing with this. You see the wave is coming in here like this, and when it passes through here, it spreads out. This is something that waves do. It's just all waves do it. Not just water waves, but sound waves, everything. And so this is called diffraction. So make a note in your notebook, because I know you always take careful notes, right, of everything we say and do in class. Okay. Diffraction is something that all waves do. And in fact, you know what you might want to do in your notes there is, let's open up a page. A good way to picture diffraction would be maybe to draw something like this. So here you've got a seawall, and here's the opening in the seawall, and you've got all the waves coming in like this. And let me draw the direction that the waves travel. Now most of the waves, they hit here on the seawall and they don't make it any further. But any wave that comes through the seawall, when it comes out the other side, it spreads out. So the direction of the wave travel goes like this. And so if I were to draw these wave fronts here, the wave fronts now are going to look like this. And the direction of the wave is going to look like this. So this is diffraction. And this is something that all waves do, not just water waves, but also sound waves as well. In fact, you guys know from experience that, you know, if you have a window here and the window's open and somebody's standing outside and they're talking really loud and you're inside trying to sleep. So this is you trying to sleep. Okay, all right. So the sound waves from this person, you know, they come like this. When they come through the window, they spread out. So even though you can't see the person, you can hear the person because the sound wave undergoes diffraction. Okay. Now, it doesn't have to be a window. It could be just a wall. And so here's the person standing right here. Okay, and so they're talking. So the sound wave is traveling out like that. Now it's traveling out in all directions, but we're interested in this wave right here. and you're standing over here. Boy, that's terrible. Let's say you're trying to sleep again. So here's you trying to sleep. Okay. All right. So even though it's not a window, it's just a wall, diffraction still happens. When this sound wave travels past the wall here, it's hard for me to, I'm using my finger. I didn't bring my pen when I came into work, so it's hard for me to write with my finger. Okay, so that sound wave doesn't just travel in a straight line. When it goes around the wall here, it comes like that. It diffracts. And so, so you on the other side of the wall, you can hear the person even though you can't see the person, all right? So now, knowing that that's what waves do, Isaac Newton looked at this picture here. Let me go back to it. Not that one, this one. Okay, so Isaac Newton recognized that if light is a wave and if all waves diffract, then we should not be seeing these sharp edges. We should be seeing fuzzy edges. But in fact, we see sharp edges. So he used that as a very persuasive argument for why light cannot be a wave. So I would recommend you write that in your notes, because you never know, it might be a homework problem, or it might even be a test problem to list the reasons why it is that people were convinced that light could not be a wave. So this is just one of the reasons. There are in fact other reasons. Let's talk about another reason, which I think is a very compelling reason here. So I want you guys to look out the window. So if you're sitting near a window right now, look out the window and tell me, is it light outside or is it dark outside? So how about, okay, looks like Taituan is saying that it's light outside. You guys agree? Okay, so Taituan, where'd that light come from? The light that you see outside your window, where did that light come from? In Utah, yeah.
The sun.
The sun, exactly right. Okay, so the light that you are seeing outside your window, that light came from the sun to the earth. Okay, now, if you guys are correct in saying that light is a wave, and I have a question that I would like to hear your answer to. So you guys know, of course, that a wave is defined as a disturbance in a medium. That is what a wave is. So like what is a sound wave? Well, it's a disturbance in the air. So when I talk to you right now, what's happening is that the air in between me and my microphone, that air is being disturbed because of my vocal cords, going forward and back and forward and back. So there's all these little pockets of high pressure, low pressure that are moving through the medium, but the wave is a disturbance in the medium. If you don't have a medium, you don't have a wave. You guys have all heard the expression, in outer space, no one can hear you scream. It was a poster for a movie way back before you guys were ever born. Okay, so outer space is empty, right? Okay. If there's no medium out there, then you can't have a wave travel through there. You need to have a medium. So I'm thinking this is a pretty darn good explanation, or a pretty darn good argument for why light cannot possibly be a wave, because if light was a wave, then you've got quite a trick trying to explain how it is that it travels through empty space in order to get from the sun to the earth. So I propose to you the light is not a wave. Wink. Okay, those of you that are taking notes, I want you to note the fact that I winked when I said that. Okay, but it is a valid argument, right? Okay, so we have two very convincing arguments for why it is the light cannot be a wave. So if it can't be a wave, well, then it must be a particle, right? Okay, well, you guys know the light actually is a wave. So how do we know that? Do any of you know what is the experiment that is really famous that proved beyond all doubt that light actually is a wave? Did it in your junior high school? Did you guys ever talk about this? Does the name Thomas Young ring a bell?
That's the slit experiment, right?
Ah, good. Okay, I knew there'd be somebody out there. Good for you, Will.
Yeah, it's from
Yes.
chemistry.
Oh, from chemistry. Ah,
Yeah.
okay. All right. Yeah. Okay. So there was a guy named Thomas Young who lived sometime after Isaac Newton did. And he thought that maybe light might still be a wave, despite these very two good arguments we just got through talking about. He was still, not convinced. And so he thought maybe light might possibly be a wave. And so he did a super famous and super important experiment called the double slit experiment. Okay, so what I'm going to do here is open up a whiteboard, and I'm going to show you kind of the experiment to the best of my limited artistic abilities. I'm going to show you what he did. Okay, so I'm going to start by taking a piece of paper. Okay, and I'm going to cut a long skinny slit here and a long skinny slit here. Okay, and then I'm going to take a light here and I'm going to shine the light onto the paper. And so most of the light is going to get blocked by the paper, but some of the light is going to go through the slit. Okay, and so Thomas Young was curious to know what would happen on the other side of the paper. All right, so this is the front view. So let's look at it from a side view. All right, so what I'm going to draw is here's the paper, and here's one of the slits, and here's the other slit. Okay, so this slit here is that opening, and this slit here is that opening. Okay. And so let's draw our light. So here is the light, and it's shining. Okay. Now, most of the light is hitting on the paper and not making it through, but some of the light is going through. Actually, tell you what, let's move this light bulb back just a little bit, because I want all the light rays to be reasonably close to being perfectly parallel. Okay, so here's all these light rays coming in from a light bulb, which is really far away. Okay, so most of the light hits the thing, doesn't get through, but some of it gets through. Now, if you were to ask Isaac Newton what it would look like if you look, let's say there's a wall right here. Okay, that's supposed to be a wall. Okay, so now remember, Isaac Newton thinks the light is made up of little bundles of particles, like little bullets of light. Okay, so if you were to ask Isaac Newton, what pattern will you see on the wall? Isaac Newton will say, well, duh, that's easy. All these little light particles are going to come through, so you're going to get a whole bunch of light particles hitting right here. You'll get a whole bunch of light particles hitting right here. Just like bullets. Imagine they're bullets going through these two windows, right? So you'll get a light spot on the bottom, you get a light spot on the top, and everywhere else will be dark. So it'll be dark up here, it'll be dark down here, and in the middle here, in between where it's in the shadow of this central region here, it'll be dark right there as well. That's what Isaac Newton would say. Well, guess what Thomas Young found? Thomas Young found that is in fact not what happens. let me switch colors here to a red pen, and let's go to the fat pen. What Thomas Young found is that in this central region right here, where Isaac Newton said, well, that's going to be hidden because it's in the shadow there, that is actually where it was bright. And this part right here where Isaac Newton said that there should be a bright spot right there, it was actually dark right there. And what gets even weirder is that if you go way up here, where you would never expect that it would be bright up there, but in fact, it would be bright up here. Now, in between would be dark. Okay, so I'll tell you what, my picture is getting a little cluttered here. Let's come with a new picture. I want a nice clean picture, and I want you guys to put this in your notes here. Okay, so here's our double slit. Okay, here's the wall. Here is the center line. Okay, so this is the region where Isaac Newton said it should be bright, and this is the other region where Isaac Newton said it should be bright. But in fact, that was not the case. What instead happened was you got a bright spot right here in the middle. So I'm going to call this let me try spelling it correctly. I'm going to refer to this as the central bright spot. And I'm probably going to have to write this several times as throughout the period. So I'm going to just abbreviate it as CBS. Boy, I just cannot write. I didn't bring my pen here. I'm writing with my big fat finger, and it's not going very well. CBS. Okay, that stands for Central Bright Spot. Okay. Oh, thank you, Sam. I could count on you to diss on me. Okay, all right, so in the center there, where we shouldn't see light, we do. And in these spots here where we should see light, we don't. And then if you come up a little bit further, then we get another bright spot. And so I'm going to call this the first diffracted. Boy, that's terrible. I want you to pretend that word spells diffracted. Okay, and then I'm going to say bright spot. Okay, so I'm going to call that the first DBS. Okay, now if there's a first DBS, well, that means there must be a second and maybe even a third and a fourth, and that is in fact what happens. Okay, so after the first diffracted bright spot, then there's another region where it's dark, and then there you go. There's the second bright spot, second DBS, and then it gets dark again, and then there's a third one, and also it's symmetrical on the bottom as well. So down here on the bottom, we've got a first DBS, first diffracted bright spot on the bottom, and then there's a second diffracted bright spot, and there's a third diffracted bright spot. Okay, and in fact, rather than just drawing it, you probably want to actually see it in real life. At least I hope you do. So let me show this to you. All right, I have a few tools here that Thomas Young did not have, so it's kind of an unfair advantage. I have a laser. He didn't have a laser. I have a piece of plastic, which I realize is going to be hard for you guys to see. Okay, so you can see that this piece of plastic is kind of transparent. You know, if I put it in front of the paper, you can still see the paper behind it, but it's a little bit darker. So you might think that this is a piece of gray plastic, but in fact, I don't think, even if I hold this close, you're not going to be able to see. Yeah, there's actually lines on here. Let me open up a whiteboard so I can show you what this looks like. Okay. So what this actually looks like is this. So here's the piece of plastic. And then if I go to a fatter pen here, so there's a fat line, and then there's a clear plastic, and then there's another fat line, and then so forth and so on. So this is called a diffraction grating. Diffraction grating. Okay, so it's just a bunch of alternating lines and spaces. All right, so that's what this thing is. So what I'm going to do is I'm going to shine a light. I'm going to shine a laser through this diffraction grating. Now, while we're at it, I have this other piece of plastic here, which I bought at a store the other day, and I had to pay a lot of money for it because the guy that sold it to me, he told me that this was a diffraction grating, but now it doesn't look like it. You see, it looks like it's totally clear. It's not even gray at all. It looks like it's completely clear plastic, but it cost me a lot of money. And the reason that the guy said that it was so expensive is because he said that it's a diffraction grating that has lines and spaces on it that are microscopically small. So basically, instead of fat lines, we've got thin lines. And instead of fat spaces, we have thin spaces. So imagine that I've got a whole bunch of lines and spaces that they're microscopic. Okay. All right. So what I'm going to do then is I'm going to shine the light through this diffraction grating and just see what happens. And while I'm at it, I'm going to shine the light through this other diffraction grating and we'll just see what happens. Okay. Now, you're going to want to see the results. So what I've done here is on the back of my chair, I have a piece of paper and you can't see it very well. Let me tilt that up a bit. Tilt it a little more still. Okay. All right, so here is the paper. And so I'm going to take my laser and I'll just shine the laser. You guys see that dot there? Okay. All right, so I'm going to stand back on the other side of my computer. All righty, so here goes. So I'm going to shine. You guys see the dot? Okay, good. All right, and then what I'm going to do is I'm going to take this diffraction grating. I'm going to put the diffraction grating in front of my laser. Now you're not going to be able to see that. So you just focus on the dot there. See if I can get that a little closer. It's about as close as we can get. All right, so there's the dot. Okay, so this is the dot without the diffraction grating. Okay, so I'm going to count down from 3, and when I get to 0, I'll put the diffraction grating in front of the laser, right? So 3, 2, 1, 0. You guys see that? It got a little bit fuzzy, but it's kind of hard to tell exactly what's happening. So I'm going to step back. So I'm going to go way behind my computer, and I'll talk loud, so hopefully you can hear. Okay, so now I'm standing way back. All right, there's the line again. And so now I'm going to try again. So 3, 2, 1. Ah, you guys see that now? Let me get even further back. Okay, I'm going to get way back. Okay, and then 3, 2, 1. Whoa, you see that? What's happening is it's spreading out, and I can't hold my hand very still very well. Okay. But so what was happening there was when I shined the laser through the diffraction grating, it spread out into a bunch of dots, very much like the ones that Thomas Young had. Okay, well, that's cool. Now, let's take this other diffraction grating, the one that I paid so much money for. I'm a little bit worried. I'm worried that I might have gotten ripped off because it certainly doesn't look like a diffraction grating to me. It looks like it's just a piece of plastic. So I'm really worried that this guy, he scammed me here. So let's see if we did. Okay, so here is the laser without the screen in front of it. So I'm going to do the same thing as before. I'm going to go 3, 2, 1, and then I'll put it in front of it, right? So 3, 2, 1, go. All right. I don't see any difference. I mean, I didn't see any difference at all. Okay. Well, maybe I just need to step back. Okay. So I'm going to step way back here. Okay. All right. So there's the light without the diffraction grating in front of it. All right. So here goes 3, 2, 1, there. Okay. So the diffraction grating, or the piece of plastic at least, is in front of it. I didn't see any difference at all. I saw no difference whatsoever. Rats. I'm thinking I got ripped off. Doggone, I hate it when that happens. Well, maybe I didn't. Okay, let's find out. So what I'm going to do is, instead of standing really far back, how about if I come close? All right, so here's my pen. I don't know if you guys can see very well. Okay, so here's my pen. And there it is. Okay, so I'm going to shine my pen on the screen. Okay, so here is the dot. Can you see the dot? So here's the dot without the diffraction grating. So let's go 3, 2, 1. There we go. Oh, hey, looky. You guys see that? There's a central bright spot and there's a diffracted bright spot on either side. Okay, so the reason I didn't see it before was I was just too far back. If I get closer like this, there you see them. And then as I move myself back, okay. So I was just back so far that I wasn't able to see the diffracted ones. If I'd come closer, there they are. So, hey, I didn't get ripped off after all. So this really is a diffraction grating. That's a relief. Okay. All right. Now, okay. Crucifix. You love this ASMR. What ASMR are you talking about there, Jackson? Have you guys been playing around while I was on the other side of
No,
the computer?
you were just real close to the mic and it was a fun experience.
Oh, because I was too close to the mic? Okay. Here, let me put my headphones back on again so that we don't get some weird reverberations. Okay, so I don't know if you guys appreciate the significance of what you just saw, but what you just saw was proof positive that light is a wave. So Isaac Newton, he never saw this experiment, but if he had, Isaac Newton would have been very troubled, because there is no way that you can explain what you guys just saw using the particle theory of light. So let me go ahead and let's open up another whiteboard. And let's talk about why this is proof that light is a wave. Okay, so here's our double slit. Okay, so hopefully you guys understand that if light was made up of little particles, okay, and so here's the wall, okay, so clearly this is what would happen is you get a bunch of light waves there, get a bunch of light waves there, get nothing anywhere else. Okay, but that's not what we saw. What we saw instead was we saw that it's bright right here, it's dark right there, and then it's bright here again, and then it's dark again, and then it's bright again. Okay, so this is what we saw. And so there's no way that the particle theory of light can explain that, but the wave theory of light explains it wonderfully, right? So let's see, if light is in fact a wave, how does that explain this? All right, well, okay. So what we're gonna do is we're gonna say, okay, light is a wave. So here's all these wave fronts. You know, think of it like you're in a helicopter up above the ocean and you're looking down. So the waves are traveling like this. The vertical lines are the wave fronts, okay? Now, when a wave goes through the opening, what happens? Well, diffraction happens. What diffraction says is that the wave spreads out. Okay, so the wave that goes through the upper opening spreads out like that, but the wave that goes through the lower opening, it spreads out too. So it comes out looking like this. Okay, and remember, these are waves, not lines. So let me change these lines. So these are waves that are coming in, and they're coming this direction here. So like that, and like that. All right. So the wave that goes through the middle there, okay, when he comes out like this as waves. And the guy from the bottom comes out as waves. All right, so let's look at what happens on the wall. So this spot right here, this thing that I like to call the central bright spot. Okay, so if you look at the wave that came there, and you look at the wave that came here, so keep in mind that they are waves, but I'm going to draw them as if they're straight lines just because it's easier to see. But remember that they're actually waves. Okay, so let me replace them with a bunch of straight lines here. So this guy here and this guy here, let's say that this distance here, I'm going to call that D1. And this distance here, I'm going to call that D2. Right? So if this guy is in the center, then hopefully you guys can see that D1 equals D2. The distance that the upper wave traveled equals the distance that the lower wave traveled. Okay. So what does the upper wave look like? Well, here's a picture of a wave, right? Okay. So let's say that the red wave is the upper wave, and let me switch to blue here for the lower wave. If both of the waves traveled the same distance, then when those two waves hit the wall, they are going to be in phase. What that means is that the peak of the blue wave and the peak of the red wave occur at the same time. So do you guys remember something called constructive interference? We talked about this before. And so now it becomes very important. Okay. If this distance and this distance are the same, then the two waves will be in phase, which means we'll have constructive interference. And so that means that we will see a bright spot right there. So far, so good? Okay, give me thumbs or give me comments in the chat box. Okay, we're good on that? Okay, I'm seeing thumbs up. Okay, good. All right, so now let's move off axis a bit. Okay, so let me I just need to clear a little room here. Okay, so let's look at what happens at some other spot on the wall. How about this spot right here? Oops, I hate it when that happens. Put that back here. Okay, all right. So let's look at this spot right here. This is the spot where Isaac Newton expected that we should see a bright spot, but Thomas Young found that we don't see anything there. It's dark there. Why is it dark there? Well, okay, let's look at the path that the light travels. So this light right here travels that distance. This light right here travels that distance. And hopefully you guys can see that D2 is greater than D1. So if we were to draw the wave, okay, so this is wave number 1. This is the wave that's coming from the upper slit. And then in blue here, I'm going to draw wave number 2. But wave number 2 had to travel a little bit farther than wave number 1 did. So they are not going to be in phase. What's going to happen is wave number 2 is going to be shifted over a little bit. Okay. And you can see that the peak of wave number 2 does not align with the peak of wave number 1. So we do not have constructive interference. What we're having is destructive interference. Okay. And in fact, if the shift is exactly the right amount, we'll have totally destructive interference. Okay. So that if wave number 2 got shifted over just by the right amount, so it starts right here. Oops, sorry, that should be blue. Try that again in blue. Okay. Okay, so here you can see that the trough corresponds with the peak. So then we have totally destructive interference. But even if it's not totally destructive, it's at least partially destructive. So the wave theory of light explains perfectly why it's dark in this region where Isaac Newton expected it should be bright. What about this guy up here? That the first diffracted bright spot. Why is it bright? Well, let's take a look at it. Okay, so let me clear some space here. Okay, so let's draw the line. So if we draw a line from the upper slit to here, and then if we draw a line from the lower slit to there, okay, so it's still true that D2 is greater than D1, but if we look at the difference, if we kind of draw a little line here so that this distance here is the same as the distance from here to there, you see we've got a little bit of extra distance here. This right here, this is the length that D2 had to travel that D1 did not have to travel. So in that case, then D2 minus D1, if that difference just happens to be exactly one wavelength, then really interesting things happen. So let's say here's the first wave. This is the wave that's coming from the upper slit, okay? And then here is the second wave, but the second wave has been shifted because it had to travel a further distance. If the amount of the shift, so this right here, this distance here, that is D2 minus D1. So if that is exactly equal to one wavelength, that's supposed to be a wavelength, not an X. Okay. If that shift distance is exactly one wavelength, then you can see that the peak of the blue wave corresponds with the peak of the red wave. And so we have constructive interference again. Okay. And so it does make sense that we're going to have a bright spot up here, just like we had a bright spot here. In this, remember, this bright spot down here occurred in the region where it should have been dark. And in fact, what about up here? What if we go all the way up here? Well, so here's D1, here's D2. Hopefully you can see in this case now, this extra path difference, the distance that the lower light had to go that the upper one did not, okay? So we got D2 minus D1. In this case, if this is the one we're talking about, it's equal to 2 times lambda. And if we keep on going up to here, let me do that in a different color. Let me do that one in green, okay? So here we got this one here. So in this case, D2 minus D1 equals 3 lambda. So the wave theory of light explains this perfectly. And so this is the experiment that proves beyond a shadow of a doubt the light actually is a wave. Okay, even Isaac Newton would have to agree with this. I mean, he would agree reluctantly, but I mean, if he looks at the data, he's going to say, yep, There's no way the particle theory of light can explain this. The only thing that can explain it is the wave theory of light. So we've proven that light is a wave. Now, we have not answered the question of whether it's a transverse wave or whether it's a longitudinal wave. And I'm not even going to attempt to answer that today. I'll save that for later. But we know that it's a wave. Okay? Now, hopefully, you guys are sitting there and saying, but wait a minute, what about those two arguments that we just talked about earlier for the reasons why it is that light cannot possibly be a wave? How do you explain that? I mean, if light is a wave, how do you explain that? Okay, so let's look at the first one. Not that one, this one. Okay, so the first argument that we had for why it is the light cannot possibly be a wave is that when we look at the edges of shadows, we see that they are sharp edges, which they should not be if light is a wave. If light is a wave, they should be fuzzy. So then how do we explain the fact that they're sharp? Well, the answer is we just didn't look closely enough. If you go in and you pick a shadow, and if you can magnify that shadow, if you look at it with a magnifying glass, you'll find out that it actually is not sharp. There actually is a little bit of fuzziness to it. And so the problem is we just didn't look closely enough. If we'd looked closely, we would have seen that it actually is sharp. Okay, so this one, not a problem. Okay, we can explain that one away really easy. But the other one is a little bit more problematic. This one, okay? This one is not so easy to explain away. So if light really truly is a wave, okay, and if it's traveling through empty space, we have a problem. Because a wave is defined as a disturbance in a medium. And that is absolutely true. So if it's traveling through empty space, how can we explain that? Anybody got any suggestions on how we can explain? If a wave needs to have a medium, how can it travel through empty space? Anybody got any suggestions? Nobody? Come on, somebody's got to have a suggestion. Ah, okay. So one person is suggesting that maybe temperature is a medium. Okay, another person is suggesting that maybe space isn't really a complete vacuum. Okay, so let's talk about that one. Okay, so it is true that empty space isn't completely empty. If you take a volume of space, 1 cubic foot of space or 1 cubic meter, I mean, this is physics, let's use the metric system. If you take 1 cubic meter of space, you will find that there, in fact, are a few molecules in there. Very few, but there are, in fact, molecules there. And so you might think, well, okay, so those are the medium. Well, not so simple. Even if you could get rid of those molecules, even if you had a box where you seal up this box and you pull out everything, all of the air, everything, and so you do not have any molecules in there at all. So it is a perfect vacuum. If this box had a window on each side and you shine a light through the window, that light would still travel through that perfect vacuum. Okay? So the inescapable conclusion is this: empty space isn't really empty. Okay, so I got to warn you guys, today is the day that we go down the rabbit hole. Have you heard that expression, Alice in Wonderland, going down the rabbit hole? And once you go down the rabbit hole, you find out that the world is really, really, really weird, right? Well, today is the day that we are going to go down the rabbit hole. So we have just proven the light is a wave, which means inadvertently, without intending to, what we've proven is that empty space is not really empty. Even if, and it's not just because of the random molecules here and there. I mean, if you've got even if it's a perfect vacuum, it's not really empty. There's something there. Now, over the years, people have come up with different names. For a while, they called it the ether, but then that fell out of favor for reasons that I don't want to go into now. So the term that is most commonly used now is they call it the fabric of the universe, or some people call it the fabric of the cosmos, but we call it fabric. So even though you can't touch it and feel it, there is something there. And that something is the medium that carries a light wave. Now, I'm not going to talk about it today or even next week or even the week after that, but about 1 month from today, we are going to start learning about electricity and magnetism. And what you're going to find is that this fabric of the universe is related to electricity and magnetism. And so it's called the electromagnetic fabric of the universe. So I'm not going to go into it today, but we'll talk about it later. So I see a couple of you are saying that your brain hurts right now. Good. I'm glad to hear that your brain hurts. That was my goal. So yay, I've succeeded. This is where physics gets fun. So from today on throughout the rest of the year, this is my favorite part of physics, is watching students' brains explode, which is kind of a problem because here you've all got your cameras turned off, so I can't see your brains explode. Not quite as satisfying as it is usual. Okay, now, for your homework tonight, you are going to have to do some problems involving this double slit experiment, where you're actually going to have to calculate some things. So you're going to need to know an equation that is called the double slit equation. And this is a really, really important equation. And you guys know by now that I think that it's our duty, it's our solemn responsibility that we have to derive the equations we use. We can't just, I can't just give you an equation and say, here's the equation, use it. That's against my religion, okay? We're gonna have to derive it. So open up open up a new page in your notebook, and up at the top, I'm going to write derivation of the double slit equation, which is the equation that you're gonna need for tonight's homework. All right, and while you're doing that, I'm gonna open up a new whiteboard. All right, and I'm going to draw a picture of the double slit. So here's the one piece of the wall, here's the other piece of the wall, and here is the final piece of the wall. So this is my slit. And I'm going to define that the distance between the slits there, I'm going to call that distance D. And over here is the wall. And I'm going to say that the distance between my double slit and the wall, I'm going to call that distance L. And right here at the midpoint, this is my central bright spot. So I'm going to call it CBS, which of course, stands for central bright spot. Okay, and then in here, this is where where Isaac Newton thought that it should be bright, but in fact, Thomas Young found out that it's actually dark right there. Let me see if I can spell the word dark a little bit better. Okay, and then right here, this is the first diffracted bright spot. So this is a bright region again. And what I'm going to do is I'm going to say that the distance between these two guys right here, I'm going to call that x. And so if I were to make a triangle here, so this would be my triangle. So this is going to be a right angle. And so this is going to be the hypotenuse. So H is probably a good letter to use for hypotenuse. All right. So I've got a nice right triangle here with sides L, X, and H. Now, I'm going to draw another triangle. So let me switch to a red pen here. And the way that I'm going to draw this triangle is not at all obvious, but if you follow, it makes sense. I'm going to draw a line from the middle of my upper slit to the first diffracted bright spot. And then I'm going to draw a line from the bottom of my bottom slit, again, going to the first diffracted bright spot. And then what I'm going to do is I'm going to draw a line right here where this line is perpendicular to the bottom line. Okay, and I'm going to make it so that this red line here and this red line right here are equal. And this little bit here, this is the D2 minus D1. Okay, so the distance from this guy to here, that's D1. The distance from this guy to here is D2. But I've drawn my line right here so that it cuts it off, so that this line that I've circled there, that is the distance, that's the difference between D1 and D2, which hopefully you guys realize that if this goes to a bright spot, the only way that it can go to a bright spot is if D2 minus D1 equals either lambda or, 2 lambda or 3 lambda. But if this is the first bright spot, that means it's lambda. If it was the second bright spot, then it would be 2 lambda. If it was the third, it'd be 3 lambda. But this is the first one, so we'll ignore those. So D2 minus D1 is equal to lambda. So far, so good. I'm going to pause for just a minute there so that you guys can finish your notes. I don't want to get too far ahead of you. All right. Okay, so now let me come back in here and redraw that little triangle. I'm going to draw it in a fat pen this time. So this now is my red triangle. And let me get rid of these. I don't want my picture to be too terribly cluttered. Okay, so I have my black triangle, which is this one. Oops, that's supposed to be black, not red, sorry. Try that again. Okay, so here's, oh, I hate it when I do that. Oh, I touched the thing to tell it that I wanted to draw, not erase, and it goes and it erases rather than draws. Okay, all right, so here we go. Okay, so here's my black triangle. And here is my red triangle. Okay. And they're both right triangles. Okay, now here's the thing that I don't have time to prove what I'm about to tell you, so I'm just going to tell you and let you guys look at it and see if you make sense. This angle right here in red and this angle right here in black, I propose to you they are equal to each other. Now, it may not be obvious at first glance, but if you go home and you think about it and just play with it, hopefully you'll realize that, yeah, it does make sense. So my red theta and my black theta are the same. So black theta equals red theta. Okay. So here's the important thing. If you accept that, which I realize, you may not be convinced that the black theta and the red theta are the same, but think about it later. And if it still doesn't come to you, we can talk about it next time we meet. But if you will agree that the black theta equals the red theta, then I propose to you that the black triangle and the red triangle, although they are different sizes, they are similar triangles. Okay? Because this angle here and this angle here are the same, and they're both right triangles, so that means they are similar triangles. So I trust that you guys remember from your math class, if you've got two similar triangles and you take the ratio of any corresponding sides, they are the same. So this side right here, that was lambda. This side right here, that's D. This side right here is L. This side right here is X. This side right here is H. So if I were to take lambda over D, so lambda over D. So lambda is the side that's opposite the angle that I know. Okay, so the corresponding side for that would be X. And then the hypotenuse, now D is the hypotenuse of the red triangle. So that means I have to take H. So lambda over D must equal X over H because of the similar triangle rule. Bingo, that's it, guys. That is the double slit equation. So I didn't do any algebra at all. This was just geometry. That is the double slit equation. Okay. Now, in your homework tonight, they're going to let you get away with a simplification, which, let's talk about this. So there's a couple situations that we could have. One is the situation that we just drew, which is this one. Okay, so this is L, this is X, this is H. But another situation that you could often have, so here's your slits. Okay. But notice this time L is very big, and sometimes X is very small. Okay. So if you look at the situation that I've drawn in red on the right, you'll notice that L is much, much bigger than X. Now that's not true over on this side. Over on this side, L and X are kind of similar in size. But if you look at the right side, you'll see that L is much, much bigger than X. If that's the case, then what you find is that L is approximately, not exactly, but approximately equal to H. Now, H is, of course, going to be a little bit longer, but I mean, if L is way bigger than X, then the difference between L and H becomes pretty much negligible. So in your homework tonight, don't be surprised if they take my equation and they simplify it. So my equation said that lambda, tell you what, let me make it in a fat pen rather than a skinny pen, because it's really important. So the equation that we derived said that lambda over D was equal to X over H. Well, in your book, when you read the book before you do the homework, because I know you always read the book before you do the homework, you're going to find that they say that this is approximately equal to X over L because L is approximately equal to H, but only if L is much, much greater than X. Okay. So although this is the rigorously correct equation, it's also acceptable in some circumstances to use this relation instead. And in your homework tonight, don't be surprised if that's what they do. Okay. So tonight's homework is actually going to be quite easy. Basically, what they're going to do is they're going to say, okay, we got these four variables right here. So if I tell you what this one is and what this one is and what this one is, can you calculate what that one is? I would hope that the answer is yes. Okay. But what they might do is they might say, okay, well, instead of telling you what lambda and D are, what they might do is they might say, okay, what I'll do is I'll tell you what L is, and I'll tell you what D is, and I'll tell you what X is, and I'll ask you to calculate what lambda is. So there's a couple ways you could do it. One way is you could say, well, this is the rigorous equation. And you could say, well, if I want to use the rigorous equation, then what I'll have to do is I'll have to recognize that H is equal to the square root of L squared plus X squared. Okay, and use that in order to figure out what H is. Or what you can do is you can just use the small angle approximation. You can say, okay, well, they told us what L is. And so you look and say, is this the case? And if it's true that that's the case, then you can just say, okay, well, I'll just let L be approximately equal to H, and then I can figure out what I need to know. Okay, so we're running short on time here. You guys good with that? So I see somebody just saying that your brain is hurting. Yeah, well, remember that everything that we just did is being recorded. So later tonight, I will post this on Canvas. Excuse me. I'll post this on Canvas so you can go back and watch this a second time. And of course, reading the book is always a good thing to do too. So I think you guys are ready for tonight's homework. So you can of course just look on Canvas and get it from there. But here it is. So before you actually start into the regular homework, what I want you to do is I want you to describe in writing the two reasons that we talked about for why people used to think that light couldn't possibly be a wave. Okay. Then after you do that, then I want you to describe in writing the experiment which proved that light actually is a wave. And then once you've done that, then go ahead and read these pages and then do these problems. And I think you'll find that tonight's homework is actually not all that difficult. Okay, now there's one other thing that we need to do before the bell rings. I hope you guys know that there's a Mars lander that is landing as we speak. So I've got the website open here. So come on. Okay. Well, apparently they haven't yet announced whether or not it landed, but you guys check in it. I mean, literally as we speak, the rover is landing. So in about 10 minutes, hopefully we'll know whether or not it was successful. Okay, so you guys, you can go ahead and type by in the chat box and I will see you next week. And I'm going to go ahead and end the meeting here.
Wait, Hendrix,
Yeah.
remember, we need to talk about my email.
Oh, yeah. So you swear on a stack of physics books that you really did send it to me?
Yeah, can I
Okay.
share my screen and show you it?
Just resend it to me. But if I didn't get it the first time,
Yeah, I'm confused. Let me read you off your email. It's dhendrix@ames.slc, right?
ames-slc.org.
Yeah, that's the one I used.
Okay, send it again. And then also send it via Canvas as well. So in fact, can you submit it via Canvas, please?
Yeah, is it still open?
Yeah, it's open. It'll be marked late, but that's okay.
Okay, awesome. Appreciate
All
it.
right. Yeah, no problem.
Thanks.
Hey, Aubrey, I see you came back here. Did you have a question?
Yeah, I had a question. I just forgot and I got off. So, on the test, it said that my score had been adjusted by 6 points.
Uh-huh.
I thought you could only get partial credit for the 5-point problems. And I only got I got the last one wrong. And Anyway, what I'm trying to say is I think you gave me 3 points extra.
Well, thank you for your honesty. I appreciate that. I'll take a look at it. And if I did make a mistake, yeah, I think I might just let you keep, as a reward for your honesty, I might let you just keep the 3 points.
Okay, thank you.
Okay. All right.
Okay.
I'll see you later.
Bye.
Bye. Hello, Simon.
Hi, I'm watching the thing right now. We made it to Mars.
We landed successfully?
Yeah, we landed successfully.
Okay,
There are
good,
2
'cause-
images in.
I just checked a couple minutes ago and it didn't say. Hey, I need to end the class here
All right.
because otherwise the recording won't work. So I'm going to end the class and then restart.